Welcome to the Neuromodulation podcast, presented to you by the International Neuromodulation Society. Dive into the forefront of today's emerging neuromodulation techniques, insights, and ethical and clinical applications. Subscribe now to join the multidisciplinary collaboration of medical care providers, scientists, and engineers who are part of the global conversation that's shaping the future of healthcare. Welcome to the Biostatistics articles live reading series, presented by the International Neuromodulation Society and developed in collaboration with the Newcastle Cognition Lab at the University of Newcastle. I'm your host, Mandy Soleil, and it's a pleasure to have you here. We're pleased to offer this ongoing series of short articles explaining how to critically apprise clinically relevant literature to evaluate evidence and inform practice. The entire series of articles is available on our website at www.neuromodulation.com/biostatistics-articles, and a direct link to this article is available in the episode show notes. We've translated each article to a live episode on the Neuromodulation podcast to bring versatility and ease to your statistics learning journey. Each primer features a single topic and an example within the context of clinical neuromodulation research and practice. Upon reading and/or listening to these articles, learners will be able to understand statistical methods, their interpretation and their limitations, identify cognitive biases to avoid inadvertently misinterpreting evidence, and interpret data for a deeper understanding of clinical research to inform clinical practice. And now, I present to you Professor Konstantin Slavin, head of the Stereotactic and Functional Neurosurgery section at the University of Illinois Chicago, or UIC, and president-elect of the INS. His term as president begins September 1st, 2024. Thank you for tuning in.
The next installment in the Biostatistics articles for the International Neuromodulation Society deals with receiver operating characteristics and the area under the curve. It is written by Alexander Thorpe, Garston Liang, and Quentin Gronau. The caveat of the chapter comes to 4 statements. The receiver operating characteristic, or ROC, curves tell us how good a predictive model, like a logistic regression model, is at differentiating between 2 possible outcomes. The second one tells you that the area under the ROC curve can be used as a measure of model performance. The third statement tells us that the higher the area under the curve, or AUC value, the better the model's performance. And finally, the fourth statement is that there is no standard interpretation for AUC values, so there is no universally good value. Part 1. Evaluating models. Predictive models are useful for understanding what factors may contribute to good or bad outcomes for patients. For example, spinal cord stimulation may have different chances of success for patients with long-term chronic pain compared to those who have only experienced pain for a short time. Let's consider a simple example study that examines this relationship with a research question: does duration of chronic pain predict pain relief after spinal cord stimulation? The researchers could use a logistic regression to find that patients with short-term chronic pain are more likely to find relief after spinal cord stimulation than patients with long-term pain. But how do our researchers know they can have confidence in their model's predictions? To answer this question, they would need to evaluate the model's performance by considering its sensitivity and specificity. Sensitivity is a model's ability to detect true positives without committing type 2 errors, saying no when the answer is really yes. Specificity is a model's ability to detect true negatives without committing type 1 errors, saying yes when the answer is really no. If the model is not sensitive, it will miss true positives. And if it's not specific, it would sound false alarms. We can assess both sensitivity and specificity of a model using receiver operating characteristic curves. Part 2. Receiver operating characteristics. Receiver operating characteristic, or ROC, curves are the way of assessing how sensitive a predictive model is. How often it says yes when the answer is really yes, over a range of specificity levels. How often it says yes no matter what the real answer is. We can think of this like a filter that starts closed and moves to being completely open. The graphs in Figure 1 show what effects these extreme positions have on the model performance. The graphs in Figure 1 show what effects the extreme positions have on model performance. On the left side of each figure, the model says no to everything, no matter what evidence it is presented with. Under these conditions, the model never gives a false positive, but it also never detects true positives. At the other extreme, the model always says yes. This means it always detects true positives, but it also gives false positives every time the answer was really no. The right proportion of yes answers must lie somewhere in between these extremes, and we do not know where. We can check every possible proportion by sweeping our filter from always no to always yes and graphing the rate of true positives against false positives at every point. If the model is no better than chance, then the true positives and false positives will increase at the same rate, signified by the left panel of the Figure 1 and the red dotted line in both panels. However, if the model is sensitive to true positives, while still ruling out true negatives, the line on our graph will curve up towards the top left of the figure. The better the model performs, the further above the dotted line it will rise. The right panel shows the better than chance model, whereas the ROC curve is above the chance level for at least some of its length. So the Figure 1 shows two examples of ROC curves, and the red dotted line represents chance level performance. The chance level on the left has an area of under curve of 0.5. The better than chance ROC on the right side has area under curve of 0.8. Greater area under the curve indicates better performance. Part 3. Area under the curve. We can boil the model's performance down to a single value by calculating the area under the ROC curve. This value simply represents the proportion of the graph that lies below the curve, depicted as a blue area in Figure 1, so it is always expressed as a unitless number between 0 and 1. However, chance level performance runs straight from bottom left to top right, so the lowest meaningful value is 0.5. Anything less than 0.5 would indicate the model's predictions are worse than just guessing. The greater the area under the curve, AUC value, the better the model's performance. This value can be used to compare the performance of multiple models. The curves in the Figure 1 are labeled with their respective AUC values. Part 4. Interpreting area under the curve. So we have a number to report. So what does it mean? Because it is proportion of correct versus incorrect classifications, we can interpret it in terms of probability when talking about a single case. A model with area under curve of 0.8 has 80% chance of correctly distinguishing between the two outcomes. Going back to our example study in which pain duration predicted success of spinal cord stimulation, we could take two randomly sampled patients, one of whose treatment brought them pain relief and one whose treatment did not. If the researcher's model produced area under the curve of 0.8, it would successfully rate the first patient's probability of treatment success as being higher than the second patient's 80% of the time. As mentioned before, the bigger area under curve is better, but there is no standard classification of area under the curves. In other words, what counts as the good area under curve depends on the context in which it is used. The researchers in our example study may be classified with 80% predictive accuracy, considering the difficulty of predicting success of treatment. However, a doctor using diagnostic tool to detect communicable disease may require a higher standard of performance due to the high cost of false negative result. The most commonly accepted interpretation from diagnostic medicine literature is anywhere below 0.7 is poor, 0.7 to 0.8 as acceptable, 0.8 to 0.9 as good, and 0.9 and above as excellent. However, these interpretations vary and should be used as a loose guide only. Further reading. Below are some open source articles that discuss receiver operating characteristics, their curves, and their interpretation in greater detail with a focus on their use in medical research. First one is by DeHond and colleagues, published in The Lancet in 2022. Another one by Mandrakar, published in Journal of Thoracic Oncology in 2019. And the third one is by Zhu and colleagues, published in Circulation in 2007. Thank you.